some discussions on entanglement in quantum field theory. I could motivate it, but I feel like I don't need to at this conference, so I'm going to skip that just for time. So I think everyone presumably thinks that entanglement entropy in quantum field theory is an interesting subject to study for whatever reason. The scope, I think mostly I'm going to focus on approaches to entanglement entropy that also potentially work at strong coupling, which means that basically I'm going to be using CFT methods. And I'll also tend to stay away from d is equal to 2, where in 2 dimensions there are many, many powerful results on entanglement entropy, but and it's a very interesting subject, but I won't talk about that. I will mostly be interested in UV finite quantities, of which entanglement entropy is not. So it shouldn't be called entanglement entropy in quantum field theory. I don't know what it should be called. And I'll also sort of mostly focus on work that I have somewhat been involved with. And the plan is today, I'll just give some background. Probably a lot of you are familiar with this background. So this is lecture 1. And the second lecture, I'll talk a little bit about the perturbative approach to entanglement entropy. And hopefully the third lecture, I'll get to the average null energy condition, so you can see a proof of the average null energy condition using entanglement methods and beyond. Okay. But this is subject to change. So background. Okay, so the standard setup for entanglement in quantum field theory is the following. So we consider a quantum field theory. It's useful to think of the Hilbert space of the quantum field theory as living on some time slice. So this is time, and we fix some slice, some Cauchy slice. And then we're interested in splitting this Cauchy slice in some way. So we have some region and its complement. And we take some state, and we're interested in some something which measures the correlations in that state between A and the complement. So the standard, well, one way to approach this problem is just to make some assumptions. So let's, for now, assume that it's okay that the Hilbert space on this slice splits as a tensor product of A and its complement. So this is the Hilbert space, which is describing degrees of freedom in here, and this is the Hilbert space describing degrees of freedom out here. And then we take some state, which is in the total Hilbert space, and then we can make a density matrix, and then we can trace over it. And the utility of tracing over it is just that now we can just think about observables in this region. So if we're just interested in what we can measure in this region, in this state, then this density matrix is sufficient. So observables, which are somehow localized in A, and then there's some tensor factor outside with a unit operator, then these guys, and often I'll just denote this OA, then the expectation value of this in the state rho, I can rewrite as just a trace over the reduced density matrix in that region. So this is good. This is sort of a standard setup. Actually, the observables that we can describe in relativistic quantum field theory are you can think of as being a little bit bigger. If I draw a space-time picture, and I'm going to suppress one of the directions, then associated to this region A, there's some causal completion of that region, which I'll call D of A. and any operator that's localized in this region, O, say, of xt, maybe on some other time slice, some t, say this is t is 0, it can also be computed with this density matrix. So this is still true. And that's because we can take this operator on this time slice, and we can think of it, we can evolve it backwards. And by causality, it will be some complicated operator, but it will always be just an operator acting on the Hilbert space of A, as long as we have causality, and as long as the operator started in this causal completion. So this region D of A is sometimes called the domain of dependence. So D of A is domain of dependence of A. And there's a really simple way to describe it. It's just all points, all space-time points, X, which are space-like from the complement region. So if I think about the complement region in that diagram, that's this here, AC, AC. And all points that are space-like separated from these regions just define this diamond. Okay. So now given this density matrix, we can compute sort of information aspects of it. So the standard thing to start with is the von Neumann entropy. So we have, or the entanglement entropy, minus trace rho A log rho A. And this, it's important to remember that this is a bad name. The entanglement entropy is a bad name. This measures, well, if this was a pure state to begin with, it measures the entanglement between A and the complement. But it might not have been a pure state to begin with. And then this will also measure the mixedness of the original state. Okay. Okay, so let me just sort of say one issue with this approach. Well, the first thing is that sometimes, can we make sense of this tensor product? And indeed, it's possible to make sense of this tensor product. So typically, what I should say first is that, let me say it this way. So you can make sense of this tensor product, but with some kind of a UV regulator. So that means I replace the Hilbert space of the quantum field theory with the Hilbert space of some theory living on a lattice. There's some UV scale, which is the lattice length. And then, then it's true that the Hilbert space is indeed a tensor product of A and A complement, as long as I'm not working in a gauge theory. But then you also find that the entanglement entropy is divergent as you send this scale, epsilon, which would be the lattice scale, to 0. So so for example, if I have a lattice regulator, so I think of the Hilbert space as living on a lattice with many sites. And then I pick a bunch of these sites, like this, and I call this region A, and then A complement is all the sites outside. Then indeed, I do have this tensor product. And so I can compute all these things. But then, in this case, what you find is the divergence. There's an area law divergence. And then there's some subleading divergences. And then there's some interesting things that arise lower order, like a log divergence and maybe some finite piece. So what this is telling us is that entanglement entropy is not a good continuum object. And so there's generally sort of two things we can do now, given this statement. So the first strategy, one, is we can subtract divergences. And the reason you might expect this is okay is because this is a UV effect. So this is because of lots of short distance correlations that arise between A and A complement. And they always live at the boundary of the region. Okay, so so they're local to the entangling surface. Yes. It depends on the state. Yeah. So I have to specify a state. Yeah, I probably should have said that here. So the state may evolve in time, in which case, yes, it will depend on time. Yeah. Okay, so and in this respect, the interesting things, well, there's this universal log piece, which is a lot of people, likely in this room, have said a lot of things about, and then the S finite piece. And for me, sort of this piece is the most interesting. The one strategy for doing the subtraction is to note, well, to note that typically, as you take the continuum limit, these short distance correlations that are giving rise to this divergence are in some sense state independent. So there's some UV thing that's happening at short distance, and the state is some IR thing. So the divergences should be the same in any given state. And so one strategy for subtracting these two things is just to take two states and take a difference. And of course, a typical state you might take is the ground state or the vacuum. So likely I'll try to stick to the convention where sigma is my vacuum state. Okay. Typically kills divergences. The other strategy is to just forget about entanglement entropy and move on and do something else. But the natural question is what replaces it. Well, there's actually many things that you can use, and I'll get to them. One thing is relative entropy, and there's a bunch of other things. But actually, the real thing that unfortunately, the real thing that replaces entanglement entropy or these kinds of ideas in quantum field theory is algebraic quantum field theory. And this is unfortunate because this is a difficult subject. Yes? Yeah, because there's some exceptions to this, but I didn't want to talk about it. Yeah, so there are some known exceptions to the state independence of these divergences. In free theories? Okay. Yeah. So Aaron knows all about these, so you can ask him. Okay. Then we can ask you. We can go to algebraic quantum field theory, and let me give a brief discussion. This is definitely not my expertise, but I would like to set up a little bit of the formalism. Okay. So the way to think about this is to forget about the density matrix and just think about observables. Okay. So in particular, we're going to consider observables that are somehow localized in some region, and we should take a causal region, right, as motivated by this discussion. So we'll take some domain of dependence of A, some causal region. And then Okay, so here we have our causal region. We have A, D of A. And then we consider OA, which somehow lives in here. And this forms an algebra. So that means that, in particular, I can take two operators that live in this region. And I'll call this algebra curly A. Yeah, so if I have two, then the product is also in the algebra, and the sum with complex coefficients is in the algebra, and also the identity is in the algebra. Okay, oh, and the dagger, that's also important. The Hermitian conjugate is also in the algebra. Now, this is a subalgebra of all operators, I'll call it this, H sigma, of operators acting on the total Hilbert space. So if I forget about this reduction and I think about just all operators, okay? So this is a subalgebra. If I take products of two, it's still an observable in here, and so forth. Sorry? Say, what's this? I'm sorry. There wasn't a question, it was just a correction. I did mean to write, it's in my notes, the tilde over the O rather than over the A, because that's confusing if I put it over the A. Thank you. Thank you very much. Okay, so this is the structure. Now, there's some technical things that I don't really want to get into. These are bounded operators, which is not actually the kind of the operators you're used to thinking about in quantum field theory, likely. So this just means that their maximum eigenvalue is bounded. And then there's some really technical things about this algebra being closed with respect to some notion of distance between operators. So closed in some topology. Okay, and then, so how does this relate to usual things that you think about in quantum field theory? Well, the usual thing you think is some field operator localized at a point, but this is not very good. It's its correlations have singularities, so this is actually, correlation functions have certain singularities, so this is a distributional field, and the way to fix that is just to smear it over some function, and you should smear it obviously in this domain so that it stays, it's some causal operator acting on A. But this is still not good because it's not bounded. Typically, if this is a scalar operator, just like x of the simple harmonic oscillator is not a bounded operator. It can go take values to infinity. But then I can do things like, so it's not bounded. But I could, exponentiate it. If this was a Hermitian operator, for example, then this is unitary. And of course, its eigenvalues are all, the magnitude of its eigenvalues are all 1. So it's bounded. Yes? So for bosons, you can do this trick. Yeah. You can take functions of these operators and make them bounded. How you actually do that in reality, yeah. Okay, so this is a little technical. Apologize for that. But okay, so once we have this structure, then we sort of throw away the reduced density matrix. What we mean by a subregion A is just the restriction to these observables. Okay. Good. And if we're interested in some density matrix, some reduced density matrix of a state, instead of saying that, we would just restrict the expectation value of these observables. Okay. And this is the density matrix on the full Hilbert space. So one important thing is that this algebra of operators, let me say this quickly, does not come from the space of bounded operators on some Hilbert space. Okay, so that's the statement that this is not a tensor product. Rather, the correct thing to do is to use something called a type 3 von Neumann algebra. And this is a very technical, difficult subject. But the one thing that you find in this type 3 von Neumann algebras is that there's no trace. You can't define the notion of a trace. And so that's sort of related to the fact that you can't define an entanglement entropy. Okay, so good. Yeah, and so the UV divergences are related to this issue, okay, whether you can define this tensor product or not. And so what we're going to do is we're going to sort of ignore this issue, and we will use a regulator. It's not going to be a lattice regulator. I'll sort of not specify it too carefully, but I'll tell you later what it is. But what I sort of think is interesting is to sort of take inspiration from this algebraic quantum field theory discussion, and then sort of restrict to things that are well defined in this limit. Okay, and so those are the things that I think are continuum objects. So restrict to well-defined notions here. And so examples are, well, it's good that the examples are actually things that you probably heard of. Relative entropy, the so-called full modular Hamiltonian, which I'll discuss later. Modular flow is a good one, and there's others. Okay. Any questions so far? Yes?
So what happens to the local operators that are at the entanglement surface? Is there any smearing that you're allowed to write down such that they're in that class?
Smearing that you write down so that they're in, are you asking about center variables or not? Well, the issue, yeah, it's sort of hard to define operators here because you have to smear them. And you have to smear them over codimension 0 region. If you try to do it over smaller codimensions, then they're not really. So I don't know. You can still have operators that live here and sort of don't live in either algebra. And sometimes it makes sense. Yeah.
So it's true that the entanglement entropy of trace of rho log rho is not well-defined, but you still have local operation class of communication that's well-defined here. So why can't we define some dimension of entanglement?
There's all sorts of discussions of this in the literature, and I may not be able to reproduce it.
Once you just get infinity if you do that?
Yeah. So what? I mean, one thing you can do is try to separate the regions, and then that gets rid of this divergence. But then it's no longer pure state entanglement, and so it's sort of harder. But that's one strategy that I've seen in this context. Okay. Good. So okay, there's another thing that comes out of this, which is quite natural, which is the notion of the commutant. we can define the commutant, which is just defined with this prime, as the algebra of all operators that commute with these operators. And in space-time, what this looks like is we have this causal diamond, we have A, and of course everything that commutes with it is associated to AC, and in particular, it's associated to the domain of dependence of AC. So this was A, and then this is D of AC. So this is really the algebra of operators for AC, which is then, if you like, the algebra of operators for D of AC. Okay. Now, there's interesting things here, though. There's certainly operators that are in neither of these algebras. Some good examples are an operator here. So not in the commutant or the original algebra, and also things like just products of two operators in the two different regions. Okay. Now there's another interesting notion, which is that of inclusion. So this is just the statement if I have some subalgebra and then I have some other subalgebra which is contained within that. So in the space-time picture, let's draw the picture where we have a region A, which is infinite. So we'll talk a lot about these semi-infinite. So we'll talk a lot about these infinite regions. So I'm going to draw some pictures for that. So this is A, and then I imagine I had, I consider a later slice, and then I split that latest time slice here into B, and so this is A complement, this is B complement, and then I can think of the domain of dependence of B, and that defines some wedge here. And all the operators here are in here. So then the notion is that the algebra is contained in that guy. And if we were thinking about how to do this in a Hilbert space language, if we made sense of this tensor product, what we would do is we'd have to pick a funny Cauchy slice, if you like. So one that would go over here, and then it would come up here, and go like this, and then we would have some C region here, and then we would consider the Hilbert space to be a tensor product of the complement of A, HC, and HB. And then this thing would just be, well, if I had some reduced density matrix acting on A, then it would go to that acting on B by tracing over C. Right. Okay, so you can do this, but in terms of this algebraic point of view, we just restrict to what things we're allowed to measure, what observables we have, and so yeah, good. And then this also, there's also a notion of causality, which is kind of obvious, but in this context, it would be interesting for us, which is the complement of this, if you like. If I consider the domain of dependence of the complement of A, so this region here, this wedge region here, then if you had this inclusion to begin with, it's pretty clear that means that this complement is now causally separated from here. So it's every point in here is space-like separated from the points in here. Okay, so D of B is contained in D of A actually implies that the algebra of B commutes with the commutant of the algebra of A. Okay, so you write it something like that. So yeah, and in words, space-like separated regions commute. Right. And so this is a basic statement of causality here. Yes. Well, okay, so this is just a way of C was just a way of thinking of this in the Hilbert space language. So that the total Hilbert space is just these three things here. If I consider the Hilbert space of stuff living on this interval here, and so you have to add this. And then you would trace over C to go from row A to row B. Whereas in this other language, you just restrict to different observables. So ones which are associated to the A region and one associated to the B region. Okay. Yeah. Yeah. Sorry. C, let me. Yeah. If that's C is just this line here. Yeah. Okay. Well, you stay away from the edge. Yeah, but you can smear operators in ways that vanish, rigorously, right? Where all derivatives vanish and so forth. Yeah, you could do that. Okay. All right. So. This is some background. Now I'm going to try and do some actual calculations. And so you'll notice that when I do the actual calculations, I'm going to forget all this and talk about tensor products, okay? Hopefully, there's sort of a missing step, but at the end of the day, what we'll do is we'll try to compute these quantities that are well-defined by this idea. And we'll see a consistency check in that we'll also find that they're finite and not divergent. When we compute that quantity, but the intermediate step we always have to do something. Okay. Questions? Okay. So this is sort of standard now. So let's talk about sort of a Euclidean description. Let me just sort of make it a heading. Euclidean methods for reduced density matrices. So how do we generate the, so let's just think about the vacuum state for now. We were interested in properties of the vacuum state, its correlations and so forth. So how do we generate the vacuum state via a Euclidean path integral? This is standard. If we just think about doing a path integral, so now this is Euclidean time, we've Wick rotated. This is still the spatial directions here. And say this is the tau is 0 slice, which was my sigma slice before. I'll take that to be my sigma slice. But now, we're really Wick rotated. Forget that. And then we consider doing a path integral on the lower half plane from minus infinity and then upwards in this direction to the tau is 0 slice. And when we do this, when we do a path integral, we always have to impose some kind of boundary conditions at the ends. So we have some field configuration, some classical field configuration associated to the fields in our path integral. And then this is just computed by this expression, x, okay, times the action. Okay, and so what does this compute? But this is just a picture of that guy. Well, it computes the overlap of the state associated to this field configuration, which is a very formal thing, but I'll just write it in any case, and the vacuum state, which I'll write as, omega. And so why does it do that? Well, that's just this fact that if I do a path integral, what I'm secretly computing is a transition amplitude, and a transition amplitude is just the time evolution of the Hamiltonian, matrix elements of the time evolution of the Hamiltonian, but in this case, it's in imaginary time, so we don't have an I here. And then if I take the limit as t, this is sort of some time where I cut it off. But if I take that time, minus t, to infinity, then this just becomes a projector onto the ground state if I sort of pull out some normalization. Okay, so that's all that's happening. this path integral is projecting onto the ground state if I don't insert anything here. Okay, so that's this guy. And now we're going to take this configuration and we're going to pretend like it has a tensor product decomposition. So take something like some phi a x tensor phi a complement. And then I want to compute, using the path integral, basically matrix elements of the reduced density matrix for the vacuum. So I want to trace over the complement, and then I want matrix elements phi of x and phi a twiddle of x. Right? And so it's not hard to see to take this picture, double it, because I need to produce a path integral both for the bra and the ket. And doing this right, the ket is this guy, and the bra is the flipped version of this guy. You put them together, you trace over the complement, and all that does is sort of join the path integral freely. So let me draw the picture here. Here is the complement region. Here is the A region. We have a path integral from above, going this way, path integral going this way. And then we're tracing over the complement, and that just lets the path integral freely go through here. But then we're imposing different boundary conditions on either end here. So that means that you have this cut here. And the path integral and the cut means that you're imposing some boundary condition, phi a twiddle here, and phi a here. Okay. And so this guy is just the trace part. And you can basically see where the issue with the UV comes from. It's what do you do here? Like that's the million-dollar question. There's some singularity happening here. I'm posing different boundary conditions above and below. At this point, it seems pretty bad. And so there's always divergences, and they're always associated to this guy. And one typical way to fix this is just to cut a hole out and impose some boundary conditions here. And this is one way to, right? And so this regulator has some scale A associated with it. And then the idea is to compute with this regulator, compute some quantity which you think should be UV finite, take the limit A, and just hope for the best. A goes to 0, yeah. Well, these are sort of on top of each other. What do you mean? Oh, this is in Euclidean time. Yeah. So the real time is sort of coming out of the board, if you like. So there's always a causal diamond associated with this region, and it's sort of, if you like, coming out of the board. I'll try and draw a picture of that in a second. Okay. Okay. Good. Okay. Yeah. Actually, right now. Okay, so if I draw a Euclidean time like this, try and draw it get a bit sharper, and then at 45 degrees to this, so this is a right angles, drawing skills, is real time coming out. And so along this plane, I have that picture. So along this plane, I have that picture. The path integrals coming in like this. And let's make the region A compact now. So I have this, and then I have the two different boundary conditions above and below. But now what I can do is I can sort of continue to do a time evolution in the real direction using, say, the path integral. And so I can move up this interval like this, something like this. on both sides. And this is schematically some unitary operator acting on row A, and the dagger of that unitary operator, where this is doing the sort of the time evolution up here. And so this is sort of a Schwinger-Keldysh picture where I have Euclidean time here, I have real time, Euclidean time, and then I might compute some operator, insert some operator here, and calculate the expectation. I put some operator here, and then sort of trace over everything, and then that joins these path integrals together. And from this picture, these pictures, you can see that that will give you the fact that for the vacuum state, or really any state, this will have the same expectation value as if I calculated it just with the pure state in the full Hilbert space. And so this is what you want a density matrix to do, and so you sort of succeeded. And this is okay, you can do this as long as you stay in the domain of dependence of A. Okay, so now we have a path integral expression for a density operator. It's a bit formal, but we have it. So we can try to compute things. So, try to compute entropies, etc. And so I want to, at this point, I want to distinguish two cases. And they're distinguished by difficulty. So let's consider two cases. So the first one is the case of what I'll call the local case. You might call it the symmetric case. It's the situation when in this Euclidean picture, you have an effective rotation symmetry around the entangling surface. Okay, so some U1 rotation symmetry. So there exists a U1 rotation symmetry which holds fixed the end point of the entangling surface, the boundary of A. And there's actually many cases like this. The symmetry could be a conformal symmetry, it could be various things. But let's just look at one case for now, which is the Rindler case. So half space Rindler cut, I don't know what you want to call it, e.g. And so, we have, this is the case if I just had flat space, my Euclidean metric, I'll write like this, plus some transverse directions, z minus 2. And then, you can Wick rotate this to real time, you just get this. But if I place my entangling surface, if I replace the region A with sort of x is bigger than 0, tau is 0, then this entangling region, in particular the boundary of this entangling region, has this U1 symmetry that holds fixed this boundary. And you can make that manifest just by going to polar coordinates in these two factors. So the x direction is important here, and sort of the y, the other d minus 2 directions are just along the entangling surface, and they'll factor out, and I often won't draw them. Okay, so right, and then we just have rotation symmetry. And the interesting thing to note is that, so that's just rotating by theta, by delta theta. Interesting thing to note is that if I Wick rotate this space, I send eta to I theta, then I get the metric of Rindler space, which is just secretly flat space. And the rotation after Wick rotation becomes a boost. So eta goes to eta plus delta eta is a boost. Okay. So rotation becomes a boost after Wick rotation. And so this rotation symmetry allows us, I'll draw it here, to slice the Euclidean path integral in a different way. So the Euclidean path integral in this situation, I'm just going to draw the x directions and the Euclidean time direction here. We have our phi a twiddle, phi a here. But instead of doing the path integral in this Euclidean time direction, I can do an angular path integral. Okay, and so this is the direction theta. And so from this picture, it's not hard to guess that the matrix elements of the density matrix, which this path integral computes, well, this path integral also computes the transition amplitude, but now in the angular direction. Well, what is the transition amplitude in the angular direction? It's just what you would sort of call the generator of rotations by an angle of 2 pi, okay? Because we're going around by 2 pi. So path integral computes is just, well, that's what it computes, and then it's not hard to see that this is just 2 pi Ka, where Ka, well, because there's no I here, remember I sort of generating some rotation by 2 pi, so I should have an I here. This operator is not the generator of rotations, it's the generator of boosts. Because I've effectively Wick rotated. Of course, this is the nicer object, so it's nice to write it in terms of this. Yeah, so it's sort of like a 2 pi I boost, if you like. So an analytic continuation of a boost. Okay, so good, and so now we have an expression for the density matrix, and it's actually pretty explicit because we know what this operator is. So what is this operator? Well, it's an integral of it's an integral over the A region. So the A region has some measure factor with a normal. So that's what this is an normal A. And then I have some killing vector, which generates the boost. So Xi killing vector, which generates the boost. This is a very fancy way to write things, but not so complicated. Where Xi is just d by d eta nu. So remember the boosts, at least in this coordinates, just look like d by d eta. And then you can rewrite it in flat coordinates, something like this. And of course, this fact that it's a killing vector just means that it solves this equation. Okay, so this is the expression for the density matrix, quite explicitly. Okay, now one thing you can do with the k, so this k is what I'm going to call the modular Hamiltonian, and I will distinguish from. This is a bit of an abuse, but I will distinguish that from something called the full modular Hamiltonian, which I'll introduce in a little bit. But some people do not refer to, yeah, I'll say that later. Okay, so, but in this form, there's one property of this that I would like to highlight, this form. So we've sort of chosen to integrate this operator on some slice A, but because this is some conserved current, because it comes from this killing vector, I can actually just move this slice around. Okay? But one thing I cannot do is I cannot change the endpoint of this integral. The endpoint is fixed, and the endpoint is the boundary of A. So let me write that in equations. So you can move the operator around. And one way to say that is, okay, so at least in Euclidean, let's say I have some, let's say I chose to integrate over here, Ka. So I have integral t dot c, maybe a bit schematic over A, but I could have also integrated it over here, over A2, so this is A1. And of course, the difference is a total derivative. So the difference is just this derivative, which is then 0 because the stress tensor is conserved. So this is equal to this, okay? Unless there's operators inserted here, in which case it's not quite true. Yeah, the important thing that I want to point out is that because you can't shift, you can move this around, but you can never shift this endpoint. And because of that, if I take an operator, some other operator, and I send it close to this endpoint, I can get singularities, okay? And so that's the statement that this operator is a bit singular. Ka is singular, and it often comes with UV divergences. Okay. All right, so this is the local case. There's a whole slew of situations where this also applies. This form of the modular Hamiltonian is very sort of general, where all I do is I replace my vector by some other killing vector, which has this property that in Euclidean it's this rotation symmetry. So some examples are, well, we just did the Rindler case, and I'm going to draw here the flow lines of the vector field C. Right, so these are the trajectories of the Rindler observables, if you like, observers, if you like. So this is Rindler. Another case is if I have a CFT and I have a ball, then I have a causal diamond associated to that ball, and there's a conformal symmetry. So now there's a conformal killing vector whose flow lines look like this. And the form of the modular Hamiltonian is the same. It's this, just with a different C. And then another case that's useful is the eternal black hole, which has a Penrose diagram like this. And then I imagine split. I'm just thinking about doing quantum fields on this background spacetime, and I split it into A and A complement. Then I can also write the reduced density matrix for this, as long as I pick, instead of the vacuum, which I don't know what that means, I pick the Hartle-Hawking state in the black hole background. Then I can tell you what the reduced density matrix is for this region. And of course, it's again the same form where the flow lines like this. Okay. All right. Any questions about that so far? Okay. All right. So this is standard stuff. Now I'm going to give, this is the sort of the density matrix interpretation of the state, the reduced density matrix. But I'd like to give sort of the state interpretation of the entanglement between A and A bar, or an A complement, in particular in the form of some kind of Schmitt decomposition. Okay, so let's talk about that now. Okay, so we're going to go back to the path integral, but instead of doing the two path integrals which made the density matrix, let's just do the state path integral. So we have this path integral with some boundary conditions, which were sort of phi a, phi complement a, and then we do it like this, in Euclidean time, and this computes this transition amplitude. But then the other way to do this was to do the path integral in the angular direction, like this, with some boundary condition here, phi a, and another boundary condition here, phi a twiddle. And so this is just evolution by pi instead of evolution by 2 pi. So this just computes matrix elements of the rotation operator by pi. Now, one important thing when you try to sort of identify these pictures, they look very similar, is to note that actually naturally in the path integral terms, this is a transition amplitude between some state in the Hilbert space of A with some other state in the Hilbert space of A. Whereas this thing is an overlap between some state including some state in the complement of A. So it's not sort of obvious how to identify these. So what we need is some way to map between these two guys. So we need some canonical map between the two configurations, phi a complement and this phi a twiddle. These two things here. And in this local case, there's always a sort of a geometric way to do that. There's an anti-unitary symmetry, always in quantum field theory, which is the Cpt operation. So we define this J to be Cp xt. So this is just charge conjugation, time reversal, and then parity. And so parity, the parity that we have to pick is just the one which sends x to minus x. And so if you do that, this is x, remember? X to minus x takes you from here over to here. And so it gives a way of identifying field configurations over here with field configurations over here. Okay. Good. So we might define J. So J acts on these two field configurations as follows. It acts on the full Hilbert space, and it gives us some conjugated field configuration, some other conjugated field configuration, where they've been flipped like this. Okay, and the conjugated field configuration is just what you would imagine. It's the complex conjugate. Remember, this is some classical field with the coordinates flipped, x to minus x, etc. Okay. So given this, we would like to identify this path integral with this path integral after acting with this conjugation. So that means we equate as follows. And so this allows us to read off this state. And I'm going to skip details because I'm sort of running out of time. But basically, you insert a complete set of states, insert the spectrum of Ka, which is something like this. And then you solve this equation. And the result is that you can rewrite the vacuum state as a sum over the spectrum of this operator I e to the minus p pi EI, so this is this pi evolution, times times I in A, and then some conjugated I in the complement, and this is just what you get when you act with this anti-unitary operator J. Okay, so this is the state. The vacuum state, written nicely. This anti-linear operator acts on this state as follows. And so notice, one thing to notice is that this is the form of a Schmitt decomposition, as I had wanted. And the anti-linear operator acts on I, A, J star. It just flips them and conjugates them. So J, A. Okay, and so with this definition, you can show that the vacuum state is invariant, and this is good because it's CPT. Right? And so CPT, you expect to leave the vacuum state invariant. Okay. Now, all right. Okay, so that's the structure here. Now, given this structure, we can go ahead and compute things like entanglement entropy. Typically, when you compute entanglement entropy, one way to do it is to compute some Renyi version. So I take rho A to the power alpha. Now, in general, we'll see later, in the non-local case, we can't do this unless alpha is an integer. But here, this is easy because all I have to do is replace e to the minus 2 pi ka with e to the minus 2 pi ka times alpha. And then in principle, I can do this trace. There's a log here. Okay, and so what you find because of that is that computing entanglement entropy in this situation is basically going to ends up this trace you compute in a space time with a conical singularity. So the picture is you have your region A somewhere here, and then at the boundary of the region A, there's a conical singularity. The angular excess here, I'll write it as an excess, even though I drew it the other way, is alpha minus 1. Okay, so then there's some singularity associated to this, and that's related to the fact that entanglement entropy is divergent, but still. You can, at least in principle, compute it and subtract the divergences and so forth. A better quantity is the relative entropy. And relative entropy takes two density matrices. And it's a way of comparing the two density matrices. It tells you how distinguishable they are. And you can write this as, well, it's defined as trace rho A and it, if it vanishes, then these two density matrices are the same. But important for us is that we can rewrite it as 2 pi times the change in the expectation value of the modular Hamiltonian associated to this state, which we'll take to be vacuum, minus the change in the entanglement entropy. So this is just the entanglement entropy of rho minus the entanglement entropy of sigma, and then this is the change in the modular energy. And so, we have this operator. We could try to calculate this using this method, and we could calculate the difference. And one thing to note is that while I told you that entanglement entropy is divergent, this quantity is maybe not so well defined. It has some issues, the change in entanglement entropy. The difference between these two is something that is totally well defined, and you always see the divergences cancel. Okay. Right. And and that's related to the fact that this operator, remember, was also a somewhat singular operator. It had divergences associated to other operators coming close to the boundary of A. So that's a related phenomenon. So that's one quantity that you can now compute, and another one another example, which is also well defined, is called the full modular operator, full modular Hamiltonian. So full modular Hamiltonian, mod ham. And this is just defined as a difference between the modular Hamiltonian for the A region, tensored with a unit operator for the complement region, minus the unit operator tensored with the modular Hamiltonian for the complement region. So this is the log of, basically the log of sigma A, and this is the log of sigma A complement. And so, one way to understand, well, in this case, the full modular Hamiltonian in the Rindler case, well, what is it? It's just an integral, the same expression that we had before, sigma nu, something like that. But now, instead of integrating over A, we integrate over the full Cauchy slice, okay? And that has the effect that now we can move the whole thing around. We don't have to keep fixed at a point. We can move the whole thing around. And so we can, that means that this is not a singular operator. In fact, it's the boost generator in quantum field theory. And yeah, good. And so, for example, it annihilates the defining state. Okay, that's sort of obvious here because it's a boost generator, and if I boost the vacuum, I shouldn't do anything. Okay. Okay, good. So this was the, okay, so this relative entropy has played, an important role in a lot of discussions of entanglement in quantum field theory, and hopefully towards the end of these lectures, I'll get to some examples of that, at which point I'll define a little bit better its properties and so forth. Okay, so this was the local case where we have a lot of structure, we can make a lot of progress. The second case is the difficult one. So I'll call that the non-local case. Partly the reason for calling it local versus non-local is that the modular Hamiltonian takes this form as an integral over a local operator. Whereas in the non-local case, that's just not true. Okay. Non-local case. So we still have some strategies that we can apply to this. We still have the Euclidean path integral. So for example, let's consider the following problem. Let's consider an excited state. And let's get that excited state by taking an operator and acting on the vacuum and putting the operator in imaginary time a little bit. So that makes this state better normalized if this is a local quantum field. So this is some excited state. It has some finite energy if you compute it, and so forth. And so, let's compute the density matrix for some subregion associated to this state. Well, how do we do that? Well, we write down a path integral, and the path integral has the following picture. There's the same cut that we had before. So this is the cut where we impose two different boundary conditions on the top and the bottom. This is sort of phi A twiddle and phi A. But now, because of this operator insertion, we have to put an operator here at minus t, and that was just for the the ket, and then I also need one for the bra. And when you take the Hermitian conjugate of some Euclidean operator, then the time flips. So this is the Hermitian conjugate of this operator. Okay. So and then so this would compute phi a, rho a, phi a. Now, okay, so once you have this, one big difference is I cannot easily calculate trace rho a to the alpha, where alpha is not an integer. So the only strategy that we have for these kind of cases is to try to compute things like trace rho to the n, where n is an integer. Of course, that's not so nice because what we really want, maybe we're not so interested in the Renyi entropies. These are the Renyi entropies, I should have said this. But these are defined so that as alpha goes to 1, I pick up the entanglement entropy as some derivative. And so, it seems like maybe we don't have access to the entanglement entropy. Okay, so but you can do this. You can compute trace rho to the n, and you do that in what's called the replica trick. So it can compute and in the replica trick. And the picture here is that we do this path integral that I just told you n times. So n is some integer that's greater than 1. So we take a bunch of copies, and then we have this cut on each of them. And it shouldn't be hard to see that computing trace rho to the n, well, that's just taking a product of n of these density matrices and tracing. Each time you take a product, you're basically identifying the top and the bottom of some slit on this integral, on this space. And so you get some complicated picture which defines some multi-sheeted space which is then branched over the boundary of the region A. So this is some multi-sheeted branched at the boundary of A. And okay, so and the important thing that I forgot here is that we would, if we're computing it in the state psi, trace rho to the n, well then we need a whole bunch of operator insertions on each of these sheets. Okay. So this is some 2n point function on some pretty crazy manifold, which I'll call Mn. And then, if you manage to do that path integral, for example, then you define then the Renyi entropies can be extracted by taking the following combination. And also I'll call this Cn. Of course, okay, so you can do this, you can do it for integer n, and the trick with this thing is well, mostly we're interested in the limit as n goes to 1 or alpha goes to 1. The trick is to try to find some analytic continuation of that function away from the integers to, say, the complex plane. And that's, that's hard. It's not even clear it's a well-defined problem. But usually you can make progress. And the thing for me about these computations, what I find interesting is that this thing is a very complicated object. It's a 2 endpoint function that we basically have no hope of constraining that because n has to be a free parameter, right? So we have to be able to compute some complicated correlation function as a function of n, and sometimes you can do it, but sometimes you can't. But if you find some tricky way to do the analytic continuation, often what happens as n goes to 1 is that the answer just depends on correlation functions on flat space, plus maybe some small corrections. And so you can actually make progress in that limit. So not only is entanglement entropy the more interesting thing, often it's, in some situations, it's the more accessible thing. It's just that you have to work a little bit hard. It's in my notes, but I was going to skip it in lieu of time. So you can read about it in my notes, which I'll post online. So there is a way to talk about this analytic continuation a little bit more systematically, but I would say that we don't have a completely rigorous discussion of that. Okay, good. Are there any questions about this? Okay. Okay, good. So there are other things you can do with this replica path integral. You don't have to compute trace rho to the n. You can compute, trace of some other density matrix, rho a, rho to the n minus 1. Nima Lashkari has sort of pioneered a lot of this stuff. And yeah. And so this, for example, is nice because when you take n to 1, then you can compute things like the modular energy of some state rather than just the entanglement entropy. Okay, okay, so I wanted to get to one sort of final point before my time runs up. Is that, okay, so this non-local case seems pretty intractable. But in terms of algebraic quantum field theory, there's sort of an interesting structure behind it. And I don't think that structure has been fully explored by us or maybe by some algebraic quantum field theory people, but maybe not by trying to actually do some computations. So let me talk about that. So in general, there's an interesting structure. Even in the non-local case. So let me just start with an example. For example, e.g., there still exists a full modular Hamiltonian. Okay, so I had defined it before for the local case, and it was just the boost operator. But I can just form this combination like this, where now this would be log or proportional to log of rho a, not the vacuum state. And this has some nice properties. For example, it still annihilates the defining state. Okay, so remember in the vacuum case, this is the boost operator acting on the vacuum, and that's sort of clear. But if I define this in terms of this state, i.e. rho a is trace of psi, so these things are the same, then it still annihilates the state. And so to see this, let's examine the Schmitt decomposition, which has the same form as this. Well, it has the same form as the form that I derived before. It is just a Schmitt decomposition, where now these are the eigenvalues of this new modular Hamiltonian, Ka. A star complement. But the states, I and I star, have the same eigenvalues, right? That's the important thing about the Schmitt decomposition. So Ka I is the same as Ka complement I star. These are the same eigenvalues. And so that means that if I take any function of Ka minus Ka complement, and I act on this Schmitt decomposition on the state psi, then I can just replace this by 0 because Ka minus Ka complement it always gives something which is 0 because these are the same energies acting on this state. So this is just f of 0. Right. And in particular, it means that this guy annihilates that state. And the other structure that's important is you can define this anti-unitary operator. J, and you just, well, it has this property that, let me write it like this. So I, A, J star, complement, just flips them and conjugates them. So J, so we still have these two operators, J and K, and they form an interesting structure. Now, I've given this discussion in terms of tensor products and so forth, but actually it's possible to define these things without reference to a tensor product. So let me do that now. So in particular, this is something that people define in algebraic quantum field theory. So the correct algebraic definition is to consider, okay, so let me define an operator which I'll call delta, which is e to the minus 2 pi k hat. And for reference, in the finite case, if I had a tensor product, this is just rho A, tensor rho A complement inverse. Okay, so that's what that is. But here it's just defined in terms of this modular Hamiltonian. Then basically we can define delta and J using the following equation. So this is an equation. It tells you there's some operator that acts on states which are acting on this defining state psi, and gives back the dagger of that operator. Okay, so this is just some fancy equation, but actually it turns out to define these two operators, J and delta. And so J has various properties. It's anti-unitary. And it has the following action on delta, where Z is some complex number. Okay, so this is a little abstract. So I'd like to sort of unpackage this a little bit by going back to the local case and to examine what it means in the local case. But I really want to emphasize that it's also true in the non-local case. So, okay. So, okay, so the first thing to examine is the following. If I take this operator delta, and this is a bounded Hermitian. Sorry, it's an unbounded, but it's positive Hermitian operator. And I take that and I raise it to some power is over 2 pi. And I act on some operator, which is then acting on the vacuum. So you can make the following manipulations. So the first thing you can do is you can add delta for free on this side. And the reason for that is that delta psi is psi. Okay, so delta leaves psi invariant, and that's for this reason that I told you up here. Okay, and now what we can do is, well, let's just be a little bit hand-wavy and go back to as if there was a tensor product. Then we can put in this form now for the vacuum state. So now, if we put in this form, we notice because this is an operator acting on OA, the complement of rho just sort of commutes through, and you're just left with the action of rho A. So this just becomes rho A is over 2 pi, rho A is psi. Okay, and over 2 pi. And then if we put back in sorry, this is sigma because it's the local case. I apologize. If we put back in what sigma is in terms of the boost operator, what is this? This is just e to the I minus I s k a OA e to the I s k a acting on the vacuum. And so what is this? This is a boosted operator. Okay? This is a boosted operator. Okay, so this is the fancy algebraic. If I erase this, put this back, this is the fancy algebraic quantum field theory way of writing a boosted operator. Now, okay, so good. So let me draw a picture of this. Let me draw a picture for reference. So in the local case, we had some A, we have some complement. And so let me draw both real time and Euclidean time. This is meant to be 45 degrees, like this. So in real time, we have this causal domain D of A. I'll just show the future of it. And if I started with an operator here, then all this does is boost the operator over here. It moves the operator over here. But now we can sort of try to interpret this equation here. So what is delta to the 1/2? Delta to the 1/2, well, if I act with delta to the 1/2, right, if I make this the same trick acting on the vacuum, then this just becomes a boost, but a boost by an imaginary amount, which is pi. So you just get pi, let me get this right, okay, A. I think I have my signs wrong. So what does this do? It takes this operator and it rotates it around by pi. So if I started with an operator over here, when acting on the vacuum, in this case, what it does is it rotates the operator over here. But that's only one way to get here, right? Remember, there's another way to get here, and that was to act with this anti-linear operator. So all this equation is saying is, okay, first rotate by pi, and then reflect back. Okay, and then I should get back to myself, and I do up to this emission conjugation, because this is an anti-linear operator. Okay, so this is a fancy equation, and that's all it means. Okay, good. And so, the J, so the important properties of this structure here is that J, OJ, takes an operator in the algebra to an operator in the commutant. And this is sort of always true. So this is the operator that reflects. This is the operation that reflects this operator from here to here. Good. But then when you come back, when you rotate back using the delta to the 1/2, you can only do that when acting on the vacuum. Otherwise, you might run into issues. So it depends. It's really important that you're acting on the vacuum. Say you had some other operator inserted over here, then you're going to have issues with time ordering and all sorts of problems. So this equation, it's really important to remember that this equation is true when acting on the state side. Okay. So this is an important thing. And the other important thing is that if I do boost by a real amount, by S, so this delta to the IS, this is also in the algebra of A. So that's kind of obvious in this boosted case because I'm just boosting this operator over here, and this is still in the domain of dependence of A. Okay, so yeah, so I just want to point out that all of these objects, full modular Hamiltonian, this anti-unitary operator J, modular flow, this is sometimes called modular flow, etc., exist in the non-local case. Okay. Do I have any time? Okay. Let me finish. I wanted to talk about the KMS condition, but I can talk about that next time. Yeah, there's time tomorrow. So yes. Okay. All right. Let me finish there.
Questions?
Yeah. No, no. Maybe if you have, yeah. I didn't know what you're thinking. Yeah. If you include this structure, then maybe in some sense, in some generalized geometry, you can think of it as a deficit. But I'm not sure. I haven't thought about it.
Okay, if there are no more questions, let's think again.